Today we're going to discuss what are some necessary and sufficient conditions for two segments, such as the black segments in this picture, to be perpendicular to one another. In fact, it turns out that there is a necessary and sufficient condition for these two segments to be perpendicular. This segment has the length A, this segment has the length B, this segment has the length C, and this segment has a length D. Then there exists a relationship between A, B, C, and D that would tell us if the two black segments are actually perpendicular. And this here is the necessary and sufficient condition, meaning that if we know that the two segments here are perpendicular, then we can say that A squared plus C squared equals B squared plus D squared. And if we know that A squared plus C squared equals B squared plus D squared, then we can claim that the two black segments are perpendicular. Here's how we can prove that this equality holds, given that we know that the two segments are perpendicular to one another. We can label this segment as x, this one as y, this one as n, and this one as m. And then we can use the Pythagorean theorem for the four right-angled triangles that we have on the picture. The Pythagorean theorem for this triangle gives us that a squared equals x squared plus n squared, which is given here. The Pythagorean theorem for this triangle gives us that c squared equals m squared plus y squared, which is given here. Similarly, we know that b squared equals n squared plus y squared, and d squared equals x squared plus m squared, which are given here. And now we can add these two equalities and add these two equalities, and we get that a squared plus c squared, given here, equals the sum of these four terms, which is x squared plus n squared plus m squared plus y squared. But this is exactly the sum of these four terms here. So it equals b squared plus d squared, the sum of the left-hand sides here. And therefore a squared plus c squared equals b squared plus d squared. And now let's think about this. If we label this angle by gamma, and we know that a squared plus c squared equals b squared plus d squared, how can we prove that gamma is 90 degrees? Of course, if this angle is gamma, we know that this angle is gamma, and this angle is 180 minus gamma, and this angle is 180 minus gamma. What we could do here is we could apply the law of cosines for this triangle, this triangle, this triangle, and this triangle. What we get are these four equalities. First, we're going to notice that cosine of 180 minus gamma here and here can be replaced by minus cosine of gamma. Hence, we get these four equalities. And now we can add the first two equalities together and the last two equalities together. We get this equality here when we add the first two equalities, and we get this equality on the second line when we add these two equalities from here. But we know that a squared plus c squared equals b squared plus d squared because we know that this equality holds. And therefore, we know that this left-hand side equals this left-hand side here. And now we can cancel out x squared, n squared, m squared, and y squared with x squared, n squared, m squared, and y squared. And then we get that this part equals this part. So we get this here. And now we can cancel out the 2's and send these terms on the other side. So we get this equality right here. We can rewrite the equality like this by taking cosine gamma and putting it in front. And then either cosine of gamma has to be 0, or the expression in the parentheses has to be 0. But the expression in the parentheses is obviously positive because each of the letters represents a distance, and the distances are always positive, and therefore cosine of gamma must be 0. Therefore, the only option for gamma is to represent 90 degrees, which corresponds to this point on the circle. And therefore, the condition a squared plus c squared equals b squared plus d squared is not only necessary, but sufficient for proving that this line and this line are perpendicular. Here's essentially the same thing, but applied to a concave quadrilateral instead of a convex quadrilateral. The diagonals of this concave quadrilateral are the two red segments, this segment and this segment, and they lie on lines that are perpendicular if and only if a squared plus c squared equals b squared plus d squared. Here's how we can prove this. If we know that this angle is 90 degrees, we can use Pythagorean theorems for this triangle, this triangle, this triangle, and this triangle. Then we get that a squared equals x plus y squared plus n squared, and c squared equals m squared plus y squared. Similarly, b squared is y squared plus n squared, and d squared equals x plus y squared plus m squared. Now, summing up these two equalities and summing up these two equalities, we get that a squared plus c squared equals the sum of these four terms, which is x plus y squared plus n squared plus y squared plus m squared. But this is exactly the sum of these four terms, so this equals b squared plus d squared. And therefore, a squared plus c squared equals b squared plus d squared if we know that this angle is 90 degrees. Conversely, if we don't know that this angle is 90 degrees, but we know that a squared plus c squared equals b squared plus d squared, we can again prove that angle gamma here is 90 degrees. We can do this by applying the law of cosines for this triangle, this triangle, and this triangle, respectively, you can see the results here. And then we can use that the cosine of 180 minus gamma here and here equals minus cosine of gamma. And then we can add these two equalities and these two equalities, use that a squared plus c squared equals b squared plus d squared here, and get that this left-hand side, which comes from the sum of this and this, equals this left-hand side, which comes from the sum of this and this. And then we can cancel out x plus y squared, n squared, m squared, and y squared, cancel out the 2's here, and then we get that cosine of gamma times, and in parentheses, x plus y times n coming from here, minus my coming from here, plus x plus ym coming from here, and minus ny coming from here, equals 0. And now we can cancel out yn with yn here, and my here with m times y here, and then what's left in the parentheses is xn plus xm times the cosine of gamma, and this equals 0. But this expression in the parentheses is always positive, therefore cosine of gamma is 0, which means that gamma is 90 degrees. Here's the optional problem. We have a triangle. This here is its orthocenter. We take the line connecting this foot of the perpendicular and this foot of the perpendicular, and we intersect it with this line here. Similarly, we take this line connecting this foot of the perpendicular and this foot of the perpendicular, and we intersect it with this line here. That's how we define this green dashed line here. We take this to be the circumcenter of this triangle, and we connect this circumcenter with this orthocenter to get the second green dashed line. We need to prove that the two green lines are always perpendicular to one another. And here's the solution. First, let's label the points. Then, since we need to prove that OH is perpendicular to FE, this is equivalent to proving OE squared plus FH squared equals HE squared plus OF squared. Let the circumcircle of ABC be K, and let its radius be R. By considering the power of E with respect to K, we get that it equals OE squared minus R squared, and it also equals EB times EA. So we can write OE squared minus R squared equals the power of E with respect to K equals EB times EA. Similarly, by considering the power of the point F with respect to the same circle, we get that OF squared minus R squared equals the power of F with respect to K equals FC times FA. By using Pythagorean theorems for triangles HME and HPF, HE squared equals HM squared plus ME squared as given here, and HF squared equals FP squared plus PH squared as given here. And now we can use these four equalities to rewrite this equality that we need to prove as follows. We need to prove that EB times EA plus R squared, which equals OE squared, plus FP squared plus PH squared, which equals FH squared, whether it equals FC times FA plus R squared, which equals OF squared, plus HM squared plus ME squared, which equals HE squared. Now the R squared cancels out, so finally what we need to prove is that EB times EA plus FP squared plus PH squared equals FC times FA plus HM squared plus ME squared. Let's label the angles in the triangle by alpha, beta, and gamma. Then we know that this length of this segment is 2r sine of beta times cosine gamma. Also, we know that this quadrilateral here is cyclic, since this angle is 90 and it equals this angle also 90. And so if this angle is alpha, this angle here is alpha. Similarly, since this quadrilateral is cyclic, since we have this angle is equal to this angle equals 90 degrees, so if this angle is alpha, this angle here must be alpha. Now, since this angle is gamma and this angle is alpha, we get that this angle is gamma minus alpha. And since this angle is beta and this angle is alpha, we get that this angle is beta minus alpha. And now we can find the lengths of the segments FC and BE by using the law of sines for the triangles FCN and BEN. Since we know the angles of these triangles, and we know the lengths of NC, which is 2r sine beta cosine gamma, and BN, which is 2r sine gamma cosine beta, we get that CF equals Cn, which is 2r sine beta cosine gamma, times the sine of alpha divided by the sine of gamma minus alpha. And we get that BE equals 2r sine gamma cosine of beta, which is the length of BN, times the sine of alpha divided by the sine of beta minus alpha. Now it's time to find the lengths of FP and EM. We can do this by applying the law of sines for triangles FNP and MEN. After all, we know the angles of these triangles, since we know that if this angle is alpha, then this angle here is also alpha, and we know that this angle is alpha, and we know that this angle is gamma minus alpha. We also know the length of Pn and Nm. Since you see, triangle PCN is similar to triangle ABC. They have the same angles, alpha, beta, and gamma. And so the ratio Pn divided by AB equals the ratio Cn divided by the corresponding side, Ca. But this is exactly cosine of gamma. And so Pn equals 2r sine of gamma, which is the length of AB, times cosine of gamma. Similarly, Mn is 2r sine of beta cosine of beta. And now by applying the law of sines for triangle FPN, we get that Fp equals, as given here, 2r sine gamma cosine of gamma, which is the length of Pn, times sine of 2 alpha, coming from this angle, 2 alpha, divided by sine of gamma minus alpha, coming from this angle, gamma minus alpha. And similarly, Me equals 2r sine beta cosine beta, which comes from the length of Mn, times sine of 2 alpha, which is this angle here, divided by sine of beta minus alpha, this angle here. Now we're going to find the lengths of EA and FA. We can do this by applying the law of sines for triangles AEN and AFN. We know the angles of these triangles. After all, this angle is beta minus alpha. This angle here is 90 degrees plus alpha. This angle is gamma minus alpha, and this angle here is again 90 degrees plus alpha. And we know the length of AN. AN equals 2r sine gamma sine beta. Therefore, EA equals the length of AN, which is 2r sine beta sine gamma, times the sine of this angle, sine of 90 plus alpha, divided by the sine of this angle, sine of beta minus alpha. Similarly, FA equals 2r sine of beta sine of gamma, which is the length of AN, times the sine of 90 plus alpha, divided by the sine of gamma minus alpha. Now we can write sine of 90 plus alpha here and here as sine of 90 minus alpha, but we also know that sine of 90 minus alpha equals cosine of alpha. Hence, this is the final expression for EA and this is the final expression for FA. The only thing left to express from this equality that we need to prove are pH and HM. But we know that pH, this is 2 times r cosine of gamma cosine of alpha, and HM is 2 times r cosine of alpha cosine of beta. So we get these two equalities. And now that we've expressed all the terms in this equality that we need to prove, in terms of r and the sines and cosines of the angles of the triangle, we can get something that we can prove. I rewrote the value of FC and put it here. Now by replacing all the terms in this equality that we need to prove by these values, we get this equality that we need to prove. Here, the first thing we could do is we could cancel out 4r squared from each of the terms. This is how we get this expression here. Now I'm going to simplify it a little bit. After the simplification, we get this equality that we need to prove. We can replace the sine squared of 2 alpha with 4 times sine squared of alpha cosine squared of alpha. Now we see that we can cancel out cosine alpha. We know that cosine squared of beta minus cosine squared of gamma equals this expression here. And 2 cosine squared beta minus 1 is cosine 2 beta, and 2 cosine squared gamma minus 1 is cosine 2 gamma. Now we can apply the formula for cosine minus cosine, and we get that the 2 cancels out, and what's left is the sine of this angle minus this angle over 2, so sine of gamma minus beta, times the sine of this angle plus this angle over 2, so sine of gamma plus beta. But we know that sine of gamma plus beta equals sine of alpha, because alpha plus beta plus gamma is 180 degrees. So, in conclusion, cosine squared of beta minus cosine squared of gamma equals sine of gamma minus beta times sine of alpha. We can get cosine squared of beta minus cosine squared of gamma from here, this minus this, taking cosine of alpha in front of the parenthesis, and inside of the parenthesis we will get cosine squared of beta minus cosine squared of gamma, which equals sine of gamma minus beta sine of alpha. And now we see that we can cancel out sine alpha. Now let's group this term, and let's group this term and this term. Or we got that proving this statement is equivalent to proving this equality here. Now note that sine of gamma equals sine of alpha plus beta, since alpha plus beta plus gamma is 180 degrees. And so this expression, sine squared of gamma minus 4 sine alpha cosine beta, can be rewritten as sine squared of alpha plus beta minus this. But sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, so this thing is squared, minus this expression, 4 times sine alpha cosine beta cosine alpha sine beta. But now see that if this thing here is A, and this thing here is B, then this thing here is 4 times AB. So essentially we get a plus b squared minus 4 times ab, which equals a minus b squared. So this whole expression can be rewritten as sine alpha cosine beta minus cosine alpha sine beta squared. And this expression gives us the formula for sine of alpha minus beta, and since sine of alpha minus beta equals minus sine of beta minus alpha, and we have a square here, we can rewrite this as sine squared of beta minus alpha. Similarly, we can rewrite this here as sine squared of gamma minus alpha. So we get this equality that we need to prove. And now we can see that we can cancel out sine squared of beta minus alpha here and sine squared of gamma minus alpha here. And then we're left to prove that sine beta cosine beta equals sine gamma cosine gamma plus cosine alpha sine of gamma minus beta. Multiplying both sides of this equality by 2, we get that this is sine of 2 beta and this here is sine of 2 gamma. So we can rewrite this equality that we need to prove like that. By applying the formula for sine minus sine, we get that this equals 2 times sine of this angle minus this angle divided by 2, so beta minus gamma, times the cosine of this angle plus this angle divided by 2, so cosine of beta plus gamma. On the one hand, we have that sine of beta minus gamma equals minus sine of gamma minus beta. And on the other hand, we have that cosine of beta plus gamma equals minus sine of alpha, since alpha plus beta plus gamma is 180 degrees. And from here, you can see that the two minuses cancel out, and we get exactly what we need to prove. Now, since this equality is true, then this equality here must also be true because we proved that they are equivalent. And therefore, the two green lines here and here must be perpendicular.